So sample problem 8.2 here is going to run through determining electron configurations and doing it kind of two ways, using full and then condensed electron configurations, as well as partial orbital diagrams that only show valence electrons. What I'm actually going to work through with you guys is I don't want to do full electron configurations. They're really kind of painful to write out. They're very extensive. Most people generally only write condensed electron configurations, so I'm going to focus just on that. And we have 3 atoms that we're going to do that for. Okay, so we'll go a little bit more slowly for the first one and then move a little bit more quickly as we move through the other ones. So potassium, again, in case you didn't know, again, potassium has atomic symbol K. It's number 19 on the periodic table in terms of its atomic number, which means it has 19 electrons. So what we're going to do here is, again, writing the condensed electron configuration. That's usually easiest to do first. What you do is you kind of find your atom wherever it is and go back to the previous noble gas, because that noble gas represents filled orbitals kind of all underneath it. So for potassium, we can write argon here. And so what we do is we write Ar in brackets here, and that tells us that we're starting with that filled shell kind of prior to that. And again, if we think about this, argon as a full kind of inner shell of electrons has 18 electrons there. And that's going to become important because one of the questions it asks us is to think about the number of inner electrons. So you can look at the kind of previous noble gas in many cases to tell you the number of inner electrons. Okay, so again, we're not talking about argon here. We need to move forward and see for potassium. So potassium is 1 more electron, and that electron is going to fill an n equals 4, L equals 0, or a 4s orbital. So we write 4s, and then we write a 1 there to indicate that there's 4 electrons. Now, to write the partial orbital diagram, that's kind of like what we did in our first problem here, where we worked with fluorine and we wrote a partial, actually wrote a full orbital diagram for that. Here we're only going to be writing it for the valence electron, so we're only writing it for this single 4s electron. So we can write one little box there for 4s, and we can put 1 arrow in there. So again, this is the condensed electron configuration, the partial orbital diagram showing only the single valence electron, and then the number of inner electrons is going to be 18. So valence electrons is 1 electron, inner electron are 18 electrons, and again the sum of those are the 19 electrons that are present in our potassium atom. All right, so pretty straightforward one there. When you have something that's kind of in one of our either group 1 or 2 or our nonmetals, they tend to be a little bit more simple than some of the stuff that's in the middle of our periodic table. Okay, so now we're going to deal with technetium, and here's technetium right here, atomic number 43. Okay, so technetium, so again, if we look at technetium, we can go back to the previous noble gas, and we're going to have krypton there. Okay, so we write Kr in parentheses there. And then we have to think about the electrons that we have there. So moving forward from krypton, we move down to our 5th row here in the periodic table, so n equals 5. So we're going to be filling this s orbital here. And maybe it's worth pointing out now, remember when we learned about s orbitals, there's only 1 of them, and then p orbitals, there's 3 of them. Well, not coincidentally, this is what we call the s block, because these are our s orbitals. There's 1, 2, 3, 4, 5, 6 that are present here in this group of 6 columns. These are our p blocks. There's 3 p orbitals, each holding 2 electrons, so that's 6 orbitals. There's our d block. Again, 10 electrons would fill these d orbitals. And then, not surprisingly, I don't even need to count here. This is 14 columns over that represent our f block. Okay, so back here to filling after krypton, we're going to be filling our 5s orbital. And if you don't remember, the d orbitals numerically follow 1 behind the p. So this is actually going to be at the 4d orbital. And then the f's are going to follow 2 behind the S's and P's. So when we put and slide these F orbitals in here, this in row 6 will actually start the 4F series. We'll actually see that in our next problem here. All right, but again for technetium, starting with krypton, we've got 5s2 and then 4d. We've got 1, 2, 3, 4, 5 electrons to get us to here. Okay, so we start with our previous noble gas, and then we're going to write 5s2, 4d5. Okay, so if we write our partial orbital diagram, our 5s orbital is completely filled. And then if I write our 4d orbital, which is the next thing that fills, I've got to have 5 boxes that are there because there's 5 orbitals. And remember, Hund's rule told us don't pair up electrons until you have to, so we're going to have 5 electrons there. I'm not going to bother showing the 5p orbital because there's nothing that's filled there. So we've got our 5s and then our 4d. And again, that's the order that gets filled there. So that's it for technetium. All right, let's do our last example here, which gets us into something that's kind of lower on the periodic table. We're going to do atomic number 82, which is lead. Okay, so again, I'm glad for this one I don't have to write. If we've got 82 electrons to fill, that's a lot of electron configuration we'd have to write just to get to xenon, which is the previous noble gas. I was pointing up there but not having this down here. We'd have lots of electron configuration to write before we'd get to xenon, which is the previous noble gas. But that's where we're going to start. We're going to start with xenon. So starting with xenon, and again moving forward, we're going to have 6s2. And then we're going to have our F block comes in here. We're going to have a completely full F block, so 4F14. And then we're going to have our 5D get completely filled because we got to get ourselves over to here. So this is going to be 6P12. Okay, so let's write that down there and then make sure we can see that on our periodic table again. So 6s2, 4f14, 5d10, and then 6p2. So again, pulling this up here, starting from xenon, we've got 6s2. The f's always follow 2 behind the p's and the d's, so 4f14, and then here's our d block. D block is completely filled, so it's going to be 5d10. The D's always follow 1 behind the S's and the P's, and then 6P2. So a lot to deal with that one. Oh, stepping back here, sorry, I forgot to mention, again, thinking of the total number of inner electrons from this one, krypton has atomic number 36, right? Atomic number 36, which means there's 36 electrons in our inner core. So we've got 36 electrons in our inner core, and then 1, 2, 3, 4, 5, 6, 7 electrons that we'll have kind of in our valence. All right, so again, thinking about lead here, again, if we want to think about this, and this we're only going to see as we get down kind of into rows 5 and 6 of the periodic table. These F and D orbitals, since they are considered completely filled, so these are filled D and F orbitals, these are considered inner electrons. Okay, so if we consider the electrons from xenon, xenon has atomic number 54. So if we're going to take 54 electrons from here, we're going to add them to the 14 electrons from the 4f orbital, plus the 10 electrons from the 5d orbital. So take all of these together, and we are actually going to have 78 inner electrons. And so if we draw what's truly considered to be valence, we're really only going to have the 6s orbitals, which house those 2 electrons, and then the p orbitals, again, having just those 2 electrons. So looking at what we have here, here's the 6s2. This block is filled, So is this block. So then we're going to have our 6p2. So again, some practice here with, I'm only going to ask you to draw condensed electron configurations. If you want to draw the full one out, you'll get credit for it. But I don't want to encourage you to have to worry about drawing out that much. It's more important to kind of recognize what core electrons are, because core electrons tend to not participate in chemical reactivity.